Okay, welcome back to the ChemDoctor, and this is a follow-up video to the video that I just completed that dealt with calculating the theoretical yield given the moles of a reactant. And what I want to do in this video is address the reactant that is in excess. All right, and what we want to do specifically is calculate the moles of NO and extend that to calculating the mass of the NO gas that actually has to react with the hydrogen. All right, and I've left all the work here that we did in the past video in order to calculate the theoretical yield of water, the mass of water produced when 0.1 moles of H2 react with an excess of NO gas. All right, so what we're going to do in this video is we're going to calculate the mass of the NO gas that was required to react with 0.1 moles of H2. Now, similar to calculating a theoretical yield, what we're going to do is utilize the moles of the reactant that we were given in the problem. So we're going to go ahead and we're going to take the moles of H2, all right, and I'm going to pull them down here. So we have 0.1 mole of H2, and what we want to do is calculate first we want to calculate the moles of NO that was required to react with the hydrogen gas. All right, so this is a similar kind of problem to trying to figure out, all right, how many tires go on a car? That's the way to think about this. All right, if H2 is a car, then you know that we need 4 tires. So that's kind of what we're doing here. So, but it's a little bit more complicated because we're dealing with moles and balanced chemical equations. So, but we utilize the same technique that we utilized in the earlier video to calculate theoretical yield of the water. So we bring the moles of the H2 down, and what we want to do is calculate using the ratio from the balanced equation, because we're in the same units in terms of the hydrogen as the coefficients from the balanced chemical equation. So we see in the balanced equation that it takes 2 moles of NO for every 5 moles of H2 gas. And notice, unit multiplier method, that the hydrogens are canceling out, and we've solved successfully for the NO. So you should get, if you're following along with a calculator and a piece of paper, you should get 0.04 moles of NO gas produced in the reaction. Now, what I want to do is get the mass of this. So we're going to need the mass of NO. All right, I'll show you how we get that right here. So if you look on a periodic table, you're going to see that the nitrogen is about 14 grams per mole. I'm just going to drop the decimals off of this. And your oxygen is 16. So the molar mass of this is going to be 14 plus 16, or 30 grams per mole. So we come back down here and we're going to multiply the moles of NO that we got by 30 grams of NO per mole of NO. And you can see again, if you're following along with the units, that moles cancels, and we've successfully solved for the moles, or excuse me, the grams. So what we get is 1.2 grams of NO gas that's used in the reaction. All right, used in the reaction. And I'm going to go ahead and label this so it's very clear. This was the mass NO used in the reaction. The mass that was used up. Now, let's talk about the law of conservation of mass, because we have essentially enough information about this problem at this point that we can apply what we've done to that thinking. All right, so what the law of conservation of mass says is that however much mass we put into this reaction as reactants. If the reaction goes to completion, then the maximum mass that we can produce has to be equal to what we put into the reaction. So let's take a look at this. All right, we've got 1.2 grams of NO that was used in the reaction. We have 0.1 moles of hydrogen that we used to initiate the reaction. So let's multiply this times its molar mass. So if you look on your periodic table, each hydrogen is worth about 1 gram per mole, dropping the decimals. All right, so in essence, we're going to multiply the 0.1 moles times 2 grams per mole, okay? And what we get out of that is going to be about 0.2 grams of H2 was funneled into the reaction. So we're going to add that to the NO, about 0.2 grams. And you can see that what we put into this reaction is 1.4 grams of total reactants. Now, if we assume that the reaction went to 100%, then we should have about 1.4 grams produced for the products. Going back, you can see that the theoretical yield of the water is 0.72 grams. So let's write that down. All right, and then we have the nitrogen, which we don't know at this point, right? It's easy enough to find it though, so let's go ahead and do that. So again, we have 0.1 mole of H2 that was used to initiate the reaction. And we see that for every 2 moles of NH3 that we would end up producing, we're going to use 5 moles of H2. And we see that ratio over here, and it's been used a few times in the problems that we're doing. So that we know we're going to get 0.04 moles of NH3 produced in this reaction. All right. The last thing we need to do then is multiply this value, the 0.04 moles of NH3 times the molar mass of nitrogen, which is actually 17 grams per mole. Now we're running this in real time, so I'm going to grab my calculator, and we have 0.04 moles times 17 grams per mole. So we're going to get, and you should follow along to make sure I'm not making any mistakes, we should get 0.68 grams of this. So coming back over to the water that was produced, we have 0.72, and we're adding that to 0.68 grams of NH3. All right, and whoops, let me get that a little bit more clear. NH3, there we go. So you should have 0.68 plus 0.72. When you add those together, lo and behold, and as it should be, we get 1.4 grams of total products that are producing. You see there's a really nice correlation to what we put into the reaction and what we got out of the reaction. All right, and with that, I'm going to go ahead and close this video.